This is the next video in a series about collision theory. We have now talked about the three facets of collision theory: collision frequency, orientation, and energy. And in the last video, we talked in more depth about energy, about what activation energy is and how to find it on the reaction diagram. And then we showed that temperature can also affect reaction energy. And so now we're going to move on to the Arrhenius equation that relates all of those things into one mathematical formula. So we can relate the three facets of collision theory. Which were collision frequency, orientation, and energy to the rate. And the person who did that was Mr. Arrhenius. And you may remember this name. We've used it once already. This is the acid-base guy. Remember, there was an Arrhenius definition for acids and bases. That was the one about the H3O plus and the OH minus. This guy was pretty busy. All right, to the Arrhenius equation. So our Arrhenius equation has K, the rate constant, has A, which is a fudge factor, and an exponential e to the power of negative activation energy over R times T. So this entire thing is an exponent from E. So let's talk about each of those pieces. So the first one is K, that's our rate constant. We're now very familiar with that. And remember, your rate constant is always a positive number. Always has to be greater than 0. A is called our frequency factor. And it's basically a fudge factor introduced to account for some of these facets of the theory and to make both sides equal. Then we have, this is E, this is 2.78 ... button on your calculator. We have EA, we know from the previous video, that's our activation energy. And that is going to be in units of joules per mole. Got our temperature. In absolute units of Kelvin. And then the gas constant rears its ugly head again. It just really seems to be popping up everywhere. And we want to use the gas constant with the joules in it. So we're going to use the 8.314 joules per mole Kelvin. So just with the formula for the root mean square speed, make sure you pay attention to the units. We need to use joules in the gas constant and also in the activation energy so that they cancel. And now we can look for the three facets of the collision theory. So we know the third facet is energy. Energy is related to this exponential term. And then our A, our fudge factor out in the front, that has to do with collision frequency and with orientation. So this formula reflects the three facets of collision theory, and we can see that temperature is also there because we know that temperature affects the energy as well. So let's focus in on this exponential factor because I think there's a lot of good information stored inside of that. So this exponent is called the energy factor because both the numerator and the denominator tell us about energy. So it's a negative activation energy over RT. So there's a negative sign. And the activation energy on the top, that represents the amount of energy that's needed to do the process. It's the minimum amount of energy that we can have for the reaction to proceed in the forward direction. And then RT on the bottom, we know this also has to do with energy. We just showed in the Boltzmann distribution in the last video that increasing the temperature increases the kinetic energy of the system. So the bottom, the denominator, represents the energy that the system has. So this exponent is really a fraction of the number that we're trying to reach and the amount of energy that we currently have. And the relationship between these two numbers will change how big the exponent is, and that will change our K. So let's do a quick examination of a variety of temperature situations. Let's bring our rough Boltzmann plot back in here. A rough plot. And we'll say our activation energy is something like here. Okay, so let's look at each of those different temperature cases and think about what this energy factor might look like. So let's say we have low temperature. So our Arrhenius equation is going to be K equals A times E to this big fraction. And we know that for the low temperature, the activation energy is a lot bigger than the energy of most of the molecules of the system. Most of the molecules of the system, here's the root mean square speed, is over here. There are very few of them with enough energy to meet the bar. So this fraction is going to be greater than 1. It's going to be a bigger number over a smaller number. Oops, we forgot the negative sign. There we go. So if we were to do this math, if you take E to a negative big number, you're going to get something that's very small. 10 to the negative 10, 10 to the negative 6, pretty small thing. And so that means our rate is going to be slow. We have a small rate constant. We're going to have a slow rate. And that makes sense with our guess from the previous video. We guessed that at low temperature, the rate would be slow because very few molecules have enough energy to climb the activation energy hill. Now we're just doing it with math. So for our high temperature situation, our Arrhenius equation looks like K equals A times E to a fraction where the denominator is closer to the size of the top. So more of the molecules, here's our root mean square speed, at least half of the molecules have enough energy. So we can say this is like a big number over pretty big. It may not be that all of the molecules have enough, but it'll be pretty close. So this number is going to be a lot closer to 1. That means it's going to be K equals A times something that's bigger than the last one at least. That means K is going to be bigger, rate is going to be faster. Just like we said before, more of the molecules have the energy that it takes to climb the mountain, so the rate is going to be faster. So that's the Arrhenius equation. In the next video, we're going to modify the equation and put it in a couple of different formats, and we're going to use it to solve for the activation energy from data.